Hola, hola chica, ¿cómo estás? Oh, is that the announcement? Minecraft Steve. Uh, Muy bien. I bet people are going to be happy about that Minecraft Steve. That's pretty cool, actually. What's the word on the internet? Are people happy with Minecraft Steve? Waluigi, yeah. Everyone wanted Waluigi. He doesn't get his chance. What people want? Master Chief. I think Master Chief would be a good sort of would be a good one. Um, who would I want to see in Smash? Um, how about what games have characters that aren't in Smash? I don't know. I have to think about it. Gonna wait for about one more person to join up. Okay, I'm gonna go ahead and get started. I hope everyone's doing well. A couple of announcements. First of all, um, I'm going out to lunch with a couple of teachers today, and so I'm moving my office hours from to 4:30 to 5:30. Okay, so if you need to come to office hours, I'll be in my Zoom room at that time. And also over the next week, my parents are visiting me. They're arriving tomorrow, and so there's a higher probability in the next week or so that I will have to move my office hours around, and I might not be as responsive as I normally am, um, just because I'm entertaining them, I guess, or hanging out with them. Um, if you look on the Canvas page, I have posted the join codes for the AP exam. So if you're thinking about taking the AP exam, underneath all the buttons on the Canvas page, it has the codes for total registration and AP classroom and all that stuff that you need. Okay? So let's go ahead and get to today's lesson. Um, Today, we are going to be talking about what are called multi-part systems. And a multi-part system, it's really easy to understand. It's just no, the AP exam is not now, but to register for it, I think the registration deadline for the AP exam is like October 30th or something like that. So if you want to register for it, um, okay. So multi-part systems, it's just a system with more than one object. Um, okay, each of these objects could have a different acceleration from every other object. They could be accelerating in different directions or have different, um, yeah. And the key thing that's going to help you solve multi-part system problems is Newton's third law. Because if we have two things that are interacting, the force that A exerts on B is equal and opposite to the force that B exerts on A. All right? So Newton's third law is crucial if you want to solve these problems accurately. Okay? So we're going to do two examples today, and then we'll transition to the Zoom room. So suppose we have a floor. Okay. And the floor is frictionless, so it has mu equals 0. There is a 3 kilogram block sitting on the ground, okay? And then on top of that is a 7 kilogram block. Between the blocks, there is friction. There is a coefficient of kinetic friction equal to 0. Let's make it 0.3. Okay? And someone is pulling on the top block only with 100 newtons of force. And that force is going to pull at an angle of 40 degrees above the horizontal. Okay? So each of these blocks is going to have a different acceleration. So we want to know, what is the acceleration of the 3 kilogram block? What is the acceleration of the 7 kilogram block? Okay? So that's the problem. We are going to only consider the moment where the 7 kilogram block is on top of the 3 kilogram block. As you might guess, because there's a big force acting on the 7 kilogram block, it's going to actually pull the 7 kilogram block off the top of the 3 kilogram block. Okay? At which point, there won't be any friction between the blocks anymore, right? Because they're not on top of each other. We're not going to consider that. We're considering these two blocks at the moment shown, where one is on top of the other. Okay? So how do we solve this type of problem? We want to start by, first of all, taking this diagonal force and breaking it up into components. So if I do that, the vertical component of the 100 Newton force is going to be 100 sine of 40, which is about 64 newtons. And the horizontal part is 100 times cosine of 40, which is 77 newtons or so. Okay. So now I'm going to do two free body diagrams. I'm going to do a free body diagram for the 7 kilogram object. Okay. And I'm going to do a free body diagram for the 3 kilogram object. Okay. So the 7 kilogram object, here's a dot representing the 7 kilogram object. The 100 Newton force is like a 64 Newton force going up and a 77 Newton force going to the right. It is sitting on top of the 3 kilogram block, so there's an upward normal force. And I'm going to call it N sub BB for between the blocks. Normal force between the blocks. The 7 kilogram block does not have a normal force from the ground because it's not touching the ground. Okay, it only has a normal force from the 3 kilogram block that it sits on top of it. Okay. We're pulling the 7 kilogram block to the right, so friction is going to point to the left, and I'm going to call it F sub BB because it is the friction between the blocks. Okay? And then there is the weight force, which is mg, going downwards. M is 7, g is 10, so 70 newtons going down. Okay, so that's the 7 kilogram block. If we look at the 3 kilogram block, it doesn't have the 100 Newton force acting on it. It has its own weight, which would be 3 times 10, 30 newtons. It has a normal force from the floor. I'll call that N sub F, because the floor is in direct contact with the 3 kilogram block. It has a normal force from the block above it. If you set something on your head, that thing pushes down on your head with its normal force. N sub BB. And actually, the size of this force has to be equal to the size of that force because they're an action-reaction pair. So this is where Newton's third law comes in, okay? The interaction between the two things obeys Newton's third law. So if you put a calculator on your head is pushing up on the calculator with a normal force. Your calculator is pushing down on your head with a normal force, and those two forces have the same size. And then the 3 kilogram block is actually going to get pulled to the right by the friction between the blocks, okay? So it's going to have friction between the blocks. And these two are an action-reaction pair. So I put a slash to indicate that this force is the same size as that force. And I put a double slash to indicate that this force is the same size as that force, but not going to be the same size in general as the normal force between the blocks, okay? Kind of like in geometry. I think you put slashes to indicate equality. All right? So this is our problem. The normal force between the blocks is going down on the 3 kilogram block because if you pile a bunch of stuff on top of you, if I pile a bunch of stuff on my head, all that stuff is pushing down on my head. The force of contact is the normal force, okay? So it's like a pincher right now because I have this stuff pushing down on my body and I have the chair pushing up on my body. So I have two normal forces from the two surfaces that are in contact with me, okay? All right. So now I'm going to write Newton's second law, which of course is net force equals m times a. And I'm going to do that for each block. And each block is going to have two Newton's second laws. It's going to have a Newton's second law in the x direction and a Newton's second law in the y direction. Okay? So in the x direction, for the 7 kilogram block, I can see that it has 77 newtons pulling to the right, and it has FBB pulling to the left. So our net force in the x direction for the 7 kilogram block is 77 minus FBB. Okay? And the net force is equal to mass times the acceleration. Oh, the mass is 7. That should be 7. Times the acceleration of the 7 kilogram block. Okay? So that's Newton's second law in the x direction. In the y direction, we have two upward forces and one downward force. So our net force is going to be NBB plus 64. Those are the two upwards. Minus the downward is minus 70. Now that has to equal the y acceleration of the 7 kilogram block, which is 0. Why? Because the block is constrained to move horizontally. It's not moving vertically. BB stands for between the blocks. F is floor, BB is between the blocks. Now, if we look at the 3 kilogram block, it has one force pulling it to the right. So its net force in the x direction is just FBB. And that's equal to 3 times the acceleration of the 3 kilogram block. So F net equals m times a. And then in the y direction, we have an upward force, normal force from the floor, and we have 2 downward forces, the normal force between the blocks, and then we have a 30 Newton force going down from the weight force. And those have to come out to 0. Why is that? Oh my gosh. Spectrum just called me. Do not want to talk to Spectrum. Once I get a phone call and they say, hello, this is Spectrum, I'm just like, click. Okay, so as I said, the 3 kilogram block is only moving side to side. It's not moving up and down. So that's why the up and down acceleration term is 0. So now we basically have a system of equations for a number of unknowns. We don't know what the friction between the blocks is. We don't know what the acceleration of each block is. We don't know what the normal forces are. So we have 5 unknowns, okay? So we just pick an equation that looks easy to solve, okay? And I'm going to solve this equation because it only has one variable, okay? So if I do that, I can see that the normal force between the blocks is 6 newtons. Okay? Normal force between the blocks is 6 newtons. Now that means that this is 6 newtons. So I have n sub f minus 6 minus 30 equals 0. So that tells me that the normal force from the floor is 36 newtons. Okay? So now, once I know the normal forces, that's going to allow me to get friction. The formula for friction is mu times normal. So the friction between the blocks is going to be the coefficient of friction between the blocks times the normal force between the blocks. So the normal force from the floor has nothing to do with the friction between the blocks. It's the normal force between the blocks that determines the friction between the blocks. So coefficient of friction between the blocks is 0.3. Normal force between the blocks is 6. So this is going to be 1.8 newtons is the friction force. Okay? So now I can go to either of these equations and I can plug in for friction. You see, so I can say 1.8 equals 3a sub 3, which says that the acceleration of the 3 kilogram block is 0.6 meters per second squared. And I can plug 1.8 here. So I have 77 minus 1.8 equals 7a sub 7. So solving that equation really quickly is going to give 10.7 meters per second squared. So there you have it. Okay, there you have it. That is how you would solve this problem. So we figured out the acceleration due to each block. So if you have any questions, type them in the live chat. If not, I'm going to continue on to another example that's similar to this. Okay, so we're going to continue with two blocks that are stacked on top of each other. We've got a 2 kilogram block with a 1 kilogram block on top of it. The coefficient of friction between the 2 kilogram block and the floor is 0.3. The coefficient of friction between the two blocks is 0.2. All right. There is a 50 Newton force pulling horizontally on the lower block. So how is this problem different? Well, it has the force is acting on a different block. It's not acting on the top block. It's acting on the bottom. It's pulling horizontally as opposed to at an angle. And it is there is also friction from the floor. Okay? So this problem is sort of analogous to, has anyone ever done that trick where you have like a tablecloth? Let's say this is my tablecloth right here, tablecloth. Here's the calculator on top of the tablecloth. And I'm pulling on the lower thing really hard. And basically, if you noticed, the calculator slides forward a little bit when I pull. Okay, so that would be the acceleration of the top block. And then my applied force is driving the acceleration of the bottom piece. Okay, so this is sort of similar to that scenario. So let's do a free body diagram of each block. Okay, so we've got the 1 kilogram block, and we've got the 2 kilogram block. For the 1 kilogram block, it is being pushed up by the normal force between the blocks. So we have N sub BB going upward. It has its weight force going downward, so that is 10 newtons. And what is making the top block move is actually the friction between the blocks is pulling, right? If I pull on the bottom block, that friction is going to pull the 1 kilogram block forward. All right? So that is the 1 kilogram block. For the 2 kilogram block on the bottom, that is kinetic friction. For the 2 kilogram block, you've got the 50 Newton force going to the right, and you actually have 2 friction forces going to the left, okay? The 2 kilogram block is being held back by the friction from the top block, which is FBB, but it's also being held back by the friction from the ground, which I'll call friction from the floor. It is getting a normal force pushing it down from the top block, so that is NBB. And it's also being pushed up from the floor. N sub F, normal force from the floor. And then it also has its own weight force going down, which is 2 times 10 or 20 newtons. Okay, so we've got a lot of different forces. I'm going to go ahead and talk about the action-reaction pairs. So FBB is an action-reaction pair, and the normal force, NBB, is an action-reaction pair. The normal force from the floor has a reaction, which would be the downward force that the 2 kilogram block exerts on the floor, but we don't really care about that because we're not analyzing the motion of the floor. We're only analyzing the motion of these 2 blocks, okay? So, once we've done our our free body diagrams, we're going to do Newton's second law in the x direction and in the y direction for each block, okay? So for the 1 kilogram block, in the x direction, it has FBB. That's the only force. So that's the net force in the x direction, and that equals 1 times the acceleration of the 1 kilogram block. Net force equals ma. In the vertical direction, we have NBB going up, and we have 10 newtons going down. So we have NBB minus 10 equals 0. Why is that equal to 0? Because the 1 kilogram block is not moving up or down. It's only moving side to side. So the vertical forces must balance to 0. So that's our 1 kilogram block, fairly simple. For our 2 kilogram block, in the x direction, we have 50 newtons going to the left, or to the right, excuse me. And then we have the 2 friction forces going to the left. So that is the net force in the x direction. There's only 3 forces in the x direction, so there's 3 terms. That equals m times the acceleration of the second block. In the y direction, we have 3 forces involved. We have the normal force from the floor going up. We have the normal force between the blocks pushing down. And we have the 20 Newton weight force pulling down. And those have to equal 0 because that block, the 2 kilogram block, is not moving up or down. All right, so now we have to solve this system of equations. Again, this is probably the easiest one to solve. It just says NBB equals 10 newtons. So the normal force between the blocks is 10 newtons. Now if I know that the normal force between the blocks is 10 newtons, I can then solve this equation. Normal force from the floor minus 10 minus 20 equals 0. That says the normal force from the floor equals 30 newtons. Boom. Once I know normal force, that's going to allow me to get friction. So the friction between the blocks is the coefficient of friction between the blocks times the normal force between the blocks. The coefficient of friction between the blocks is 0.2. The normal force between the blocks is 10. So we get 0.2 times 10, or 2 newtons. That is the friction between the blocks. Okay. The friction from the floor is going to be the coefficient of friction with the floor times the normal force from the floor. Okay. Coefficient of friction with the floor is 0.3. Normal force from the floor is 30. So our friction is going to be 9 newtons, is the friction from the floor. So let me label all this stuff on the diagram. So normal force between the blocks was 10, which means that that was 10. Normal force from the floor was 30 newtons. We got the friction force between the blocks is 2 newtons. This is also 2 newtons. And then the friction from the floor is 9 newtons. All right. So now we're in the home stretch. Friction between the blocks is 2. So that says that the acceleration of the 1 kilogram block is 2 meters per second squared. Okay. Substituting in for FBB and gives 50 minus normal force between the blocks, which is 2, minus or friction force between the blocks, which is 2, minus friction force from the floor, which is 9, equals 2a. So that says what? 39 equals 2a. So that's going to be what? 15, or 39 over 2 is going to be 19.5 meters per second squared is the acceleration of the second block. Okay. So there is a question about static or kinetic friction. One of the things I want to say about this type of problem is you can have a lot of different things happening. You can have static friction or kinetic friction. You can have friction goes to the left or to the right. You can, and so really what you have to do if you want to solve the problem is you have to make an assumption. And if you solve the problem without any sort of contradictions, then, you've found the solution, okay? So if you say, assuming that this is kinetic friction and that's kinetic friction, I found a solution, and that solution is consistent, then you found the right solution. But if you get a contradiction, then that means one of your assumptions was incorrect, and you need to redo the problem, changing your assumptions about how the forces are behaving. So it can get really complicated, and the number of complications increases as you have more objects, okay? Let me give you an example. What if this force wasn't 50 newtons? What if it was 10 newtons? Okay? What if it was 10 newtons? Well, my equations would be exactly the same, but this would be 10. Okay? And so what I would get for the net force would not be 50 minus 2 minus 9. It would be 10 minus 2 minus 9. So the net force would be negative. Okay? And so basically you pull on this bottom block with 10 newtons of force, and it's like you're saying it has a negative acceleration. So you're pulling one way and it accelerates the other way. Like, that doesn't make any sense whatsoever. So there must be some sort of an inconsistency with what you're saying. So probably the inconsistency is that you have static friction. Okay? So I'd have to go back and say, well, it's actually static friction, and then redo the entire problem. So there can be some complications with this, but I'm going to give you some clear-cut stuff because this is your first time encountering this type of problem. All right? So I will see everybody in the Zoom room.